Fundamentals of HVACR, Chapter 8, Types of Energy and Their Properties. Objectives include: explain the relationship among energy, work, and power, explain the difference between potential and kinetic energy, explain common forms of energy, distinguish between non-renewable and renewable energy sources, perform energy conversion calculations, and describe the law of conservation. Diagram the electrical distribution system and explain natural gas distribution. Describe standard and SI units of work and power, and describe energy efficiency measurements. At its most fundamental level, heating and air conditioning is about controlling energy. Understanding energy and how it affects the world is crucial to understanding heating, air conditioning, and refrigeration. Many tasks performed by air conditioning technicians involve controlling and measuring energy. Thermometers are used to measure thermal energy levels. Energy makes matter move, changes its temperature, and even changes its physical state. Work is done when energy is transferred into an object. This energy transfer results in the object being moved, heated, or physically changed. Power is the rate at which work is accomplished. Mechanical work is defined as force multiplied by distance. Moving a weight of 1 pound a distance of 1 foot requires 1 foot-pound of mechanical work. Power is the rate at which work is accomplished. Because it is a rate, time is involved. 1 horsepower is equal to moving 33,000 pounds a distance of 1 foot in a period of 1 minute. Energy can be classified as either potential or kinetic. Potential energy is energy that is stored, waiting to perform work. Kinetic energy is energy in motion, actually performing work. Examples of potential energy include a compressed spring or water held in a reservoir behind a dam. Releasing the spring releases the mechanical energy by putting the spring in motion, converting potential energy into kinetic energy. Releasing the water through a spillway in the dam converts the water's potential energy into kinetic energy because the water is in motion. Heat, or thermal energy, is associated with molecular motion. Molecules move slowly at cold temperatures and quickly at warm temperatures. A change in thermal energy that results in a change in temperature is called a sensible heat change because a temperature change can be sensed. Heat is also associated with the physical state of matter. It takes a lot of heat to change matter from one physical state to another. Gas has the highest energy level, solid has the lowest energy level, and liquid is in between. A change in heat that results in a change of state is called latent heat, meaning hidden heat, because the change cannot be sensed with a thermometer. That's because when something changes state, its temperature stays the same. Chemical energy is the energy change that takes place when the atoms of materials rearrange themselves to form entirely new materials from the same atoms. Batteries are an example of chemical energy. A chemical change in the materials of the battery creates electrical potential. Batteries are an example of electrical potential energy. Electricity is the flow of electrons. Electricity is the mainstay of heating and air conditioning systems. The controls are all electrical, and many of the systems use electricity exclusively for their power source. Electrical current flow in a circuit is an example of kinetic energy. Electrons move from one atom to another in a chain reaction which carries through the wire, creating an electrical current. Magnetic energy is created by the alignment of electrical charges. This alignment gives the entire object a polarity that sets up an invisible magnetic field. Magnetic energy is used to transfer mechanical energy into electrical energy, or electrical energy into mechanical energy. All electric motors used in air conditioning use a magnetic field to turn an electric current into mechanical energy. Many controls that operate motors also rely on magnetism to turn electrical energy into mechanical energy. Non-renewable energy sources have a limited supply. Currently, most of the world's energy is supplied by non-renewable energy sources. The world's growing energy demands have strained the current methods of retrieving and distributing these non-renewable sources. The increasing energy demands of the world cannot be supported indefinitely, as we are using up finite resources of energy at an ever-increasing rate. Renewable energy sources are energy sources that can be replenished. Interest in renewable energy sources is increasing as researchers look for long-term solutions to the world's energy appetite. Some of the renewable energy sources that have been explored include solar, wind, hydro, ocean, geothermal, and biomass. The most highly developed renewable energy sources include solar and wind. Operating appliances, heating and cooling our homes, and transporting people and goods all depend upon energy conversion. Energy can be converted from one form to another. The purpose of an electrical power plant is to convert existing forms of potential energy, such as coal or natural gas, into electrical energy. These conversions are not perfect. Some energy is lost with each conversion. But energy is not really lost. Some of it is just not directed towards the desired outcome. The lost energy is actually just channeled into a form of energy that was not intended. Most often, this is heat. Energy conversions can be reversed. Heat can be used to generate electricity, and electricity can be used to generate heat. Most of the energy we use is produced in a central location and distributed throughout the country. The two forms of energy used most in heating and cooling are electricity and natural gas. The laws of physics work against distributing large amounts of electrical power over long distances. Power lines have resistance. The longer the wire is, the higher its electrical resistance. Electrical work is done by a combination of current and voltage. Voltage loss is calculated by multiplying current times resistance. To reduce the voltage loss through the line, it is necessary to reduce the current traveling through it. This is done by increasing the voltage. For example, let's compare two ways of delivering 1 kilowatt of electrical power. We could deliver 1 amp at 1,000 volts or 10 amps at 100 volts. For the sake of argument, we'll say the resistance of the conductor, the wire carrying the electricity, is 5 ohms. That's really fixed by the type of wire and its length. The loss of power at 1 amp would be 5 volts, calculated as 5 ohms times 1 amp. The loss of power at 100 volts would be 50 volts, 10 amps times 5 ohms. Now look at the percentages. The 1 amp system, we lost 5 volts out of 1,000, so we delivered 99.5% of the voltage. The 10 amp system at 100 volts, we lost 50 volts out of 100, so we lost half of our power, delivered only 500 watts out of 1,000 watts, so we delivered only 50% of what we sent. That is why electricity is distributed at very high voltages, to minimize the loss through the power lines. Alternating current is used for our power distribution because it is much easier and cheaper to accomplish the required voltage changes. The voltage is changed or transformed through a device called a transformer. The voltage is increased to send it long distances and then decreased as it gets closer to the end user. Looking at the diagram of a typical voltage distribution system, we see that the voltage is generated somewhere in the neighborhood of 20,000 volts. This is already pretty high, but then it's stepped up through large overhead transmission lines as high as 765,000 volts. Along the way, it passes through substations, which reduce the voltage. In this example, the first reduction is to 69,000 volts. The diagram shows an industrial plant that has its own substation, which reduces the volts to 440. Another substation reduces the voltage to 13,800 before it enters a neighborhood. Finally, pole transformers reduce the voltage to 120/240 going to houses. Natural gas is collected, refined, and distributed through a nationwide network of pipelines. While large gas consumers, like electric utilities and industrial plants, may get their gas directly from the main pipeline, most users rely on local distribution networks. Mechanical work is accomplished when an object is moved. Mechanical work is measured by the weight of the object and how far it is moved. A foot-pound is the product of multiplying the weight in pounds times the distance in feet. Moving a weight of 1 pound a distance of 1 foot requires 1 foot-pound of mechanical work. Torque wrenches are used to measure the amount of mechanical work put into turning a bolt. Standard torque wrenches are calibrated in foot-pounds. A Newton meter is the product of multiplying the force in newtons times the distance in meters. SI torque wrenches are calibrated in Newton meters. Temperature is a comparative measurement. It compares the concentration or level of heat against known standards. For example, the temperature of water when it freezes or boils. The freezing point on the Fahrenheit scale is 32 degrees, while the freezing point on the Celsius scale is 0 degrees. The boiling point on the Fahrenheit scale is 212 degrees, while the boiling point on the Celsius scale is 100 degrees. It is important to understand that temperature does not measure the amount of heat in an object. Instead, temperature measures the concentration of heat. Heat quantity, or the amount of heat, is measured in thermal units. Some thermal units include BTUs, calories, or joules. To illustrate the difference between temperature and BTUs, we can discuss the difference between concentration and quantity. So looking at the bottle on the left, it has 2 drops of red coloring in it, but it looks redder to the eye. It has a higher concentration of red, but less quantity of red coloring. The bottle on the right, on the other hand, has 6 drops of red in it, but because it has more water and the 6 drops are spread across more water, it does not look as red to the eye. It has a lower concentration of red, so it's less red looking, but it actually has a greater quantity of red coloring. So the higher concentration would represent temperature, whereas the higher quantity would represent BTUs. BTU stands for British Thermal Unit. British thermal units were used in the traditional English measurement system. A BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. A calorie has a similar concept to the BTU, the amount of heat required to raise a specific quantity of water 1 degree. The calorie was part of the early metric system. A calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. A kilocalorie is actually 1,000 calories. The calorie that we count in food is really a kilocalorie. Thermal units based on a temperature change of water are slightly inaccurate because the amount of heat required to produce the change does not remain constant. Today, joules are more commonly used as thermal units of work in the SI system because the amount of work represented by a joule is constant. A joule is the thermal equivalent of mechanical work. A joule is roughly equal to 4 calories. Electrical work is measured in watt-hours. To measure the quantity of electrical work, it is necessary to measure both how long the work is being performed and at what rate in watts. Watt-hours are calculated by multiplying watts times hours. Watts is a measure of the rate at which electrical work is done. The watt is defined as 1 amp of current flowing at a potential difference of 1 volt. A watt-hour is working at the rate of 1 watt for the duration of 1 hour. A watt-hour is the amount of electrical work done at the rate of 1 watt for a period of 1 hour. Because the watt-hour is a very small amount of work, most electrical work is measured in kilowatt-hours. A kilowatt-hour is equal to 1,000 watt-hours. Power companies charge customers for kilowatt-hour usage. A joule is a heat equivalent for mechanical work. Joules today are used in the SI system for all forms of energy. The joule is a work done by the force of 1 Newton moving a 1 kilogram object 1 meter. Consuming electrical power at the rate of 1 watt for 1 second is the electrical equivalent of a joule. Power is a rate of doing work. Power measures the amount of work accomplished over a period of time. All power measurements involve time. Horsepower is a rate of doing mechanical work. 1 horsepower is defined as producing 33,000 foot-pounds of mechanical work in 1 minute. Thermal power can be measured in BTUs. The amount of heat required to raise 1 pound of water 1 degree Fahrenheit in a period of an hour is 1 BTU hour. In the United States, the output of furnaces and air conditioners is rated in thousands of BTUs per hour. A common rating for refrigeration equipment in the United States is the ton. A ton of cooling is defined as the amount of cooling accomplished by melting a ton of ice over a 24-hour period. This works out to 288,000 BTUs in a 24-hour period. 144 BTUs to melt 1 pound times 2,000 pounds of ice equals 288,000 BTUs per day. However, it's more common to think of the rate per hour rather than the rate per day. If we divide this 288,000 BTUs per day by 24 hours, we get 12,000 BTUs per hour, which is what is normally meant as a ton of refrigeration. Depending upon the time interval you want to use, a ton of cooling is either 288,000 BTUs per day, 12,000 BTUs per hour, or 200 BTUs per minute. Watts is a measure of the rate at which electrical work is done. Wattage depends on both voltage and current. A watt is defined as a current of 1 amp flowing at a potential of 1 volt. The formula for watts is amps times volts. Wattage measures the rate at which electrical work is accomplished. Although the watt was originally conceived as a unit of electrical power, it is used today as the standard SI unit of power for all types of power. The watt is a rate of power equal to 1 joule of energy per second. Watts are also used for thermal power in the SI system. For example, the output of furnaces and air conditioners in most countries besides the United States are rated in kilowatts. The energy efficiency ratio, EER, is the number of cooling BTUs per hour that a unit produces for every watt of electricity used. EER is determined by dividing a unit's cooling capacity in BTUs per hour by the energy used in watts. EER is a steady-state measurement taken at design conditions. Seasonal energy efficiency ratio, SEER, tests the operation at more than one condition to simulate seasonal operation. The seasonal energy efficiency ratio, SEER, is the number of cooling BTUs per hour that a unit produces for every watt used over a season. A unit's SEER is typically higher than its EER. The Heating Seasonal Performance Factor, HSPF, measures the efficiency of heat pumps. The HSPF is the number of heating BTUs per hour that a unit produces for every watt of electricity used over a season. Readings are taken at several operating points to simulate seasonal operation. A heat pump's HSPF is typically lower than its SEER. Energy is the ability to do work. Work is the amount of energy transferred. Power is the rate of energy transfer. The difference between work and power is that work is a quantity while power is a rate.